For these first types of factoring problems, we can do exactly what we've been doing in the past and still get to the right answer. So I want to show that first just to show you that you don't need to have the pattern necessarily if you see one of these perfect square trinomials like they are in A and B of this classwork. So if I just approached it like I've approached every other trinomial problem with A equals 1, here I can just say I'm going to start by making my two parentheses. After I make my two parentheses, I'm going to bring down x and x. I'm going to bring down the first sign. This second sign tells me same or different. Same as the first plus is an additional plus. Now I'm looking for two things that multiply to 36 and add to a positive 12. The ways to multiply to 36 are 1, 36, 2, 18, 3, 12, 4, 9, and 6, 6. So when I'm looking for the one that adds to 12, if I add them together, this would be 37, this would be 20, this would be 15, 13, and 12. The one that adds to 12 is a 6 and a 6, so I put the first one there, second one there, and that is the correct factored form of x squared plus 12x plus 36. Another way of writing x plus 6 times itself would just be writing x plus 6 quantity squared. Because when I put that squared, it means something times itself. So again, I can get to this correct answer, x plus 6 times x plus 6, by using the methods that we've been using all along. That said, there's a shortcut here. If you recognize that taking half the middle term and squaring it gets you to the last term, then it becomes whatever the variable is, whatever half the middle term is, as a factor being squared. So since half of 12x is 6x, this becomes x plus 6. Again, it only works if after taking half, when you square it, you get to the last number. And this first x has to be an understood 1 to use this method. If I go to problem B and I just try and use this pattern and fit it to this pattern, negative 14x, half of negative 14x would be like taking negative 14, dividing it by 2. That would give me negative 7. If I then took negative 7 and squared it, negative 7 times negative 7 would give me positive 49. That tells me that these match up with my pattern for a perfect square trinomial. So I can just write it as parentheses, whatever the variable is, whatever half the middle term is, so half the middle term is negative 7, and then make it quantity squared. For everything in 6.4 that's a trinomial like this, it's going to have this pattern. So hopefully that makes it easier when you're doing this homework. When you get to the test, same questions on the sample test will be like this on the real test for the most part. I think there might be sprinkled in between these two concepts. But basically when you get these trinomials, there are quicker ways to do it if you recognize it. Again, you can always do it the same way we've been doing it. For the second type of problem that we're focused on in this lesson, it's a new concept, but again, it's about fitting a pattern. So here you're going to have problems where there's two things that are squares and there's a subtraction sign between them. It's called difference of squares. What you really need to identify is what's the first thing being squared and what's the second thing being squared. So I'm going to call A the first thing being squared. In this first position, to get to x squared, we're taking x and multiplying it by itself. In the second position is a 25. To get to 25, the square root of 25 would be 5, telling me that 5 times itself is what gets me to 25. For that reason, this difference of squares problem is going to factor to A plus B, A minus B. So if you can identify what's being squared in the first term, what's being squared in the second term, and there's a minus sign between them, it just factors to first term plus second term minus second term. Or I should say square root of first term plus square root of second term times square root of first term minus square root of second term. For this problem D, identifying the same things, the thing being squared first is a t, the thing being squared second is a 1. So I can write this as t plus 1, t minus 1 when factoring that difference of squares. Again, in part E, we have a number that's a square minus another square. I can identify them. To get to 9, I would need to multiply 3 by itself. To get to c squared, I need to multiply c by itself. So this becomes root of the first term 3 plus root of the second term c times root of the first term 3 minus root of the second term c. This one's a little trickier just because the first term has both a number and a variable with it. So I'm kind of going to do each of those separate when I'm identifying what times itself gets me to 25y squared. I'm going to start with the coefficient 25. I know that 5 times itself gets me to 25. I'm then going to look at the variable and say to get to y squared, I need to multiply y by itself. So really the entire first term's root is 5y. For the second term, it's a 16. I know that 4 times itself gets me to 16. I then set this up the way I have the ones above. I write the first term square root, which was 5y, plus the second term root, which was 4, the first term root, 5y, minus the second term root, 4. When we get down to g, we have 2 different variables to worry about. To get to this, x squared, we had to multiply x by itself. To get to this 4y squared, to get to the 4, we need to multiply 2 by itself, and to get the y squared, we need to multiply y by itself. So the whole term 2y is what's being multiplied by itself to get me to 4y squared. That means I can factor this as first term root x plus second term root 2y, first term root x minus second term root 2y. For h, we have 100a squared minus 81b squared. Apologies that we're reusing this a and b. That said, my first term, or a in terms of the difference of squares formula, is 100, the square root of which is 10, a squared, the square root of which is a. Then we have the minus sign that we need, and we have 81, the square root of which is 9, b squared, the square root of which is b. That's why when I go to factor, I have first term 10a plus second term 9b times first term 10a minus second term 9b. This is the correct factored form. So the overall formula that we're using for difference of squares is some term a is being squared minus some term b that's being squared must factor to a plus b, a minus b. These are pretty much the same type of problem as we just did. It's just a slightly different instruction. Factor the expression completely. So for this first one, v squared plus 4v plus 4. This is another example of one of those perfect square trinomials. If I take half of 4v, really I'm taking 4 divided by 2. That would give me a positive 2. If I squared that positive 2, it would get me back to 4. So this is the proper format. When we do that, we can just make it whatever the variable is, whatever half the middle term is. In this case, half of 4 was a positive 2, and then square that term. Just to show you that this formula does work, if I do it out, v plus 2 times v plus 2, I would write it as double distribution, v times v plus 2 times v plus 2, v times v plus v times 2 plus 2 times v plus 2 times 2. V times v is v squared, v times 2 is 2v, 2 times v is 2v, and 2 times 2 is 4. When I combine the middle term, 2v plus 2v, this v squared stays, these two v's combine to give me a total of 4v, and then I still have this plus 4, which was exactly where we started. So this is the proper factored form. This is why it's a perfect square trinomial. Again, as long as you get to this answer, or this is the same thing as v plus 2 times v plus 2, I'm fine with however you get there, whether it's by recognizing the pattern or just traditional method of factoring. This problem's the hardest one in the problem set. It's not in the proper order, so the first thing that I'd want to do is reorder it. X squared term, which is 9x squared, plus middle term, which is 30x, plus last term, which is 25. I absolutely could do this by the cross method, but since it's in the section that's on perfect square trinomials, I know that it's going to be a perfect square, so what I'm really going to do is identify what the square root of the first term is, what the square root of the second term is, or I'm sorry, of the last term, and then say it's going to be those two being multiplied by itself. So bear with me here. I can't just take half the middle term and say what would that be squared, because it doesn't take into account this 9. So this is a special case. I only gave you one problem like this that's multiple choice on the homework. That said, let me show you how I'm getting to my answer. Basically, I'm taking the squared term and I'm putting it under a square root and saying, what's the square root of 9x squared? Square root of 9, something times itself that gives me 9 is 3. Square root of x squared, something times itself that gives me x squared is x. If I do it with the final number in the sequence, 25, the square root of 25 is 5. Since it comes from this section, I know that this answer is going to be 3x plus 5 times 3x plus 5. To check that that's true, I can do out my math. I can say this is really double distribution, 3x times 3x plus 5 times 3x plus 5. I can continue and say this is really 3x times 3x plus 3x times 5 plus 5 times 3x plus 5 times 5. 3 times 3 gives me 9, x times x gives me x to the second power. Plus 3 times 5 gives me 15x. 5 times 3 also gives me 15x. And then 5 times 5 gives me 25. Final step, leave the x squared term the same. Combine the like terms, the 15x and the 15x. That gives me 30x. And then include the plus 25 at the end. Again, we can get back to where we began. So I understand that this last one in this problem set is a little difficult. Again, there's multiple choice answers. Worst case scenario, you can just multiply the different answer choices together and see which one gets you back to the problem that they're asking.